I'm going to talk today about energy and climate. And that might seem a bit surprising because my full-time work at the Foundation is mostly about vaccines and seeds, about the things that we need to invent and deliver to help the poorest 2 billion live better lives. But energy and climate are extremely important to these people. In fact, more important than to anyone else on the planet. The climate getting worse means that many years their crops won't grow. There'll be too much rain, not enough rain. Things will change in ways that their fragile environment simply can't support. And that leads to starvation, it leads to uncertainty, it leads to unrest. So the climate changes will be terrible for them. Also, the price of energy is very important to them. In fact, if you could pick just one thing to lower the price of to reduce poverty, by far you would pick energy. Now, the price of energy has come down over time. Advanced civilization is based on advances in energy. The coal revolution fueled the Industrial Revolution, and even in the 1900s, we've seen a very rapid decline in the price of electricity. That's why we have refrigerators, air conditioning. We can make modern materials and do so many things. And so we're in a wonderful situation with electricity in the rich world. But as we make it cheaper, and let's go for making it twice as cheap, we need to meet a new constraint. And that constraint has to do with CO2. CO2 is warming the planet. And the equation on CO2 is actually a very straightforward one. If you sum up the CO2 that gets emitted, that leads to a temperature increase. And that temperature increase leads to some very negative effects. The effects on the weather, perhaps worse, the indirect effects in that the natural ecosystems can't adjust to these rapid changes, and so you get ecosystem collapses. Now, the exact amount of how you map from a certain increase in of CO2 to what temperature will be and where the positive feedbacks are, there's some uncertainty there, but not very much. And there's certainly uncertainty about how bad those effects will be, but they will be extremely bad. I asked the top scientists on this several times, do we really have to get down to near zero? Can't we just cut it in half or a quarter? And the answer is that until we get near to zero, the temperature will continue to rise. And so that's a big challenge. It's very different than saying, we're a 12-foot high truck trying to get under a 10-foot bridge and we can just sort of squeeze under. This is something that has to get to zero. Now, we put out a lot of carbon dioxide every year, over 26 billion tons. For each American, it's about 20 tons. For people in poor countries, it's less than 1 ton. It's an average about 5 tons for everyone on the planet. And somehow we have to make changes that will bring that down to zero. It's been constantly going up. It's only various economic changes that have even flattened it at all. So we have to go from rapidly rising to falling and falling all the way to zero. This equation has 4 factors, a little bit of multiplication. So you've got a thing on the left, CO2, that you want to get to zero. And that's going to be based on the number of people, the services each person's using on average, the energy on average for each service, and the CO2 being put out per unit of energy. So let's look at each one of these and see how we can get this down to zero. Probably one of these numbers is going to have to get pretty near to zero. That's back from high school algebra, but let's take a look. First, we've got population. The world today has 6.8 billion people. That's headed up to about 9 billion. Now, if we do a really great job on new vaccines, healthcare, reproductive health services, we could lower that by perhaps 10 or 15%. But there we see an increase of about 1.3. The second factor is the services we use. This encompasses everything: the food we eat, clothing, TV, heating. These are very good things. Getting rid of poverty means providing these services to almost everyone on the planet. And it's a great thing for this number to go up. In the rich world, perhaps the top 1 billion, we probably could cut back and use less. But every year, this number on average is going to go up. And so overall, that will more than double the services delivered per person. Here we have a very basic service. Do you have lighting in your house to be able to read your homework? And in fact, these kids don't, so they're going out and reading their schoolwork under the street lamps. Now, efficiency, E, the energy for each service, here finally we have some good news. We have something that's not going up. Through various inventions and new ways of doing lighting, through different types of cars, different ways of building buildings, there are a lot of services where you can bring the energy for that service down quite substantially. Some individual services even bring it down by 90%. There are other services like how we make fertilizer or how we do air transport where the rooms for improvement are far, far less. And so overall here, if we're optimistic, we may get a reduction of a factor of 3 to even perhaps a factor of 6. But for these first 3 factors now, we've gone from 26 billion to at best maybe 13 billion tons. And that just won't cut it. So let's look at this 4th factor. This is going to be a key one. And this is the amount of CO2 put out for each unit of energy. And so the question is, can you actually get that to 0? If you burn coal, no. If you burn natural gas, no. Almost every way we make electricity today, except for the emerging renewables and nuclear, puts out CO2. And so what we're going to have to do at a global scale is create a new system. And so we need energy miracles. Now, when I use the term miracle, I don't mean something that's impossible. You know, the microprocessor is a miracle. The personal computer is a miracle. The internet and its services are a miracle. So the people here have participated in the creation of many miracles. Usually we don't have a deadline where you have to get the miracle by a certain date. Usually you just kind of stand by and some come along, some don't. This is a case where we actually have to drive at full speed and get a miracle in a pretty tight timeline. Now I thought, how could I really capture this? Is there some kind of natural illustration, some demonstration that would grab people's imagination here? I thought back to a year ago when I brought mosquitoes, and somehow people enjoyed that. It really got them involved in the idea of, there are people who live with mosquitoes. So with energy, all I could come up with is this. I decided that releasing fireflies would be my contribution to the environment here this year. So here we have some natural fireflies. I'm told they don't bite. In fact, they might even not even leave that jar. Now, there's all sorts of gimmicky solutions like that one, but they don't really add up to much. We need solutions, either one or several, that have unbelievable scale and unbelievable reliability. And although there's many directions that people seeking, I really only see 5 that can achieve the big numbers. I've left out tide, geothermal, fusion, biofuels. Those may make some contribution, and if they can do better than I expect, so much the better. But my key point here is that we're going to have to work on each of these 5, and we can't give up any of them because they look daunting, because they all have significant challenges. Let's look first at the burning fossil fuels, either burning coal or burning natural gas. What you need to do there seems like it might be simple, but it's not, and that's to take all the CO2 after you've burned it, going out the flue, pressurize it, create a liquid, put it somewhere, and hope it stays there. Now, we have some pilot things that do this at the 60 to 80% level, but getting up to that full percentage, that will be very tricky, and agreeing on where these CO2 quantities should be put will be hard. But the toughest one here is this long-term issue. Who's going to be sure, who's going to guarantee something that is literally billions of times larger than any type of waste you think of in terms of nuclear or other things? This is a lot of volume. So that's a tough one. Next would be nuclear. it also has three big problems. Cost, particularly in highly regulated countries, is high. The issue of the safety, really feeling good about nothing can go wrong, that even though you have these human operators, that the fuel doesn't get used for weapons. And then what do you do with the waste? Although it's not very large, there are a lot of concerns about that. People need to feel good about it. So three very tough problems that might be solvable and so should be worked on. The last three of the five I've grouped together. These are what people often refer to as the renewable sources. And they actually, although it's great they don't require fuel, they have some disadvantages. One is that the density of energy gathered in these technologies is dramatically less than a power plant. This is energy farming. So you're talking about many square miles, thousands of times more area than you think of as a normal energy plant. Also, these are intermittent sources. The sun doesn't shine all day, it doesn't shine every day, and likewise the wind doesn't blow all the time. And so if you depend on these sources, you have to have some way of getting energy during those time periods that it's not available. So we've got big cost challenges here. We have transmission challenges. For example, say this energy source is outside your country. You not only need the technology, but you have to deal with the risk of the energy coming from elsewhere. And finally, this storage problem. And to dimensionalize this, I went through and looked at all the types of batteries that get made for cars, for computers, for phones, for flashlights, for everything, and compared that to the amount of electrical energy the world uses. And what I found is that all the batteries we make now could store less than 10 minutes of all the energy. And so, in fact, we need a big breakthrough here, something that's going to be a factor of 100 better than the approaches we have now. It's not impossible, but it's not a very easy thing. Now, this shows up when you try to get the intermittent source to be above, say, 20 to 30% of what you're using. If you're counting on it for 100%, you need an incredible miracle battery. Now, how we're going to go forward on this? What's the right approach? Is it a Manhattan Project? What's the thing that can get us there? Well, we need lots of companies working on this. Hundreds. In each of these five paths, we need at least 100 people. And a lot of them you'll look at and say, they're crazy. That's good. And I think here in the TED group, we have many people who are already pursuing this. Bill Gross has several companies, including one called eSolar that has some great solar thermal technology. Vinod Khosla investing in dozens of companies that are doing great things and have interesting possibilities, and I'm trying to help back that. Nathan Myhrvold and I actually are backing a company that perhaps surprisingly is actually taking the nuclear approach. There are some innovations in nuclear, modular, liquid, and innovation really stopped in this industry quite some time ago. So the idea that there's some good ideas laying around is not all that surprising. The idea with TerraPower is that instead of burning the part of uranium, the 1%, which is the U-235, we decided, well, let's burn the 99%, the U-238. It is kind of a crazy idea. In fact, people had talked about it for a long time, but they could never simulate properly whether it would work or not. And so it's through the advent of modern supercomputers that now you can simulate and see that, yes, with the right materials approach, this looks like it would work. And because you're burning that 99%, you have greatly improved cost profile. You actually burn up the waste, and you can actually use as fuel all the leftover waste from today's reactors. And so instead of worrying about them, you just take that. It's a great thing. It breeds this uranium as it goes along. So it's kind of like a candle. You can see it's a log there, often referred to as a traveling wave reactor. In terms of fuel, this really solves the problem. I've got a picture here of a place in Kentucky. This is the leftover, the 99%, where they've taken out the part they burn now, so it's called depleted uranium. That would power the US for hundreds of years. And simply by filtering seawater in an inexpensive process, you'd have enough fuel for the entire